Space is often portrayed as majestic, silent, and endlessly beautiful. From Earth, it looks calm, an ocean of stars stretching beyond imagination. But beyond our atmosphere lies one of the most hostile environments known to science. Space is not empty, gentle, or forgiving. It is violent, cold, irradiated, and governed by forces that can destroy the human body in seconds. Unlike dangers on Earth, space does not allow second chances. There is no breathable air, no stable temperature, and no natural protection from radiation or extreme gravity. Even the most advanced spacecraft and spacesuits are only thin barriers between life and immediate death. Here are some of the most extreme and most painful ways a human could die beyond Earth. Solar radiation, death from invisible fire. Stars are colossal nuclear reactors. They give off light and heat that sustain life, but they also produce violent outbursts known as solar flares. These eruptions release massive amounts of charged particles and high-energy radiation that can travel across space at nearly the speed of light. If a spacecraft were caught in the path of a powerful solar flare, the damage would begin almost instantly. Sensitive electronics would fail first. Communication systems would go dark. Navigation would be lost. Within moments, radiation would begin penetrating the hull itself, passing through metal, circuitry, and human tissue alike. Inside the body, radiation shatters DNA at the molecular level. Cells lose the ability to repair themselves. Organs begin to fail simultaneously rather than one at a time. Victims would experience sudden nausea, dizziness, and overwhelming weakness. As radiation exposure continues, the brain struggles to maintain consciousness, while the immune system collapses. In extreme cases, organ failure could occur in under 5 minutes. While loss of consciousness might come before complete oxygen depletion, the damage would already be irreversible. Death would not be dramatic, but relentless and unavoidable. Some stars, particularly volatile red dwarfs like Proxima Centauri, are known to unleash flares thousands of times stronger than those typically produced by our Sun, making nearby space exceptionally dangerous. Gravity wells, when escape becomes impossible. Gravity dominates the structure of the universe. Every massive object creates a gravitational well, a region of space where nearby objects are pulled inward. The larger the object, the deeper and more dangerous that well becomes. If a spacecraft drifts too close to a massive planet or star, its engines may no longer be powerful enough to counteract gravity. At that point, the ship is no longer navigating, it is falling. As the descent accelerates, extreme G-forces build rapidly. Blood is forced away from the brain toward the lower body. Vision narrows, then fades completely. Consciousness is lost long before physical impact. If the object is a gas giant, the danger multiplies. As the ship plunges into the atmosphere, pressure rises violently. Temperatures climb to thousands of degrees. Winds move faster than any hurricane on Earth. The spacecraft would be torn apart long before reaching any solid core, ejecting its occupants into a storm of crushing force, toxic gases, and heat intense enough to vaporize metal. Against gravity on this scale, there is no recovery, only acceleration toward destruction. Atmospheric re-entry. Re-entering a planet's atmosphere is one of the most dangerous phases of spaceflight. At orbital speeds exceeding 28,000 kilometers per hour, even thin atmospheric particles become lethal obstacles. As a spacecraft hits the upper layers of an atmosphere, friction converts speed into heat almost instantly. This heat can exceed 2,000 degrees Celsius, hot enough to melt steel. Heat shields are designed to absorb and redirect this energy, but even minor failures can be catastrophic. If a heat shield cracks or burns unevenly, the temperature inside the cabin begins rising within seconds. Electronics fail, structural integrity weakens. Turbulence shakes the ship violently as air pressure fluctuates unpredictably. Eventually, the hull ruptures. Air rushes out. Decompression follows. The combination of extreme heat, loss of oxygen, and structural collapse leaves no chance of survival. Even planets that might otherwise be considered habitable, such as Kepler 22b, become deadly if entry conditions are not perfectly controlled. Orbital debris. Death by space shrapnel. Earth is surrounded by a growing shell of human-made debris. Defunct satellites, rocket fragments, and collision remnants orbit the planet at speeds exceeding 8 kilometers per second, faster than rifle bullets. There are tens of thousands of tracked objects large enough to destroy a spacecraft, and millions of smaller fragments that cannot be reliably monitored. At orbital velocity, even a paint chip can punch through reinforced hulls. A direct collision would cause explosive decompression. Air would escape violently, dragging unsecured objects, and potentially crew members, into space. Even if the impact does not destroy the ship outright, the resulting damage could render life support systems unusable within seconds. This threat is growing due to Kessler syndrome, where debris collisions generate even more debris, increasing collision risk exponentially and potentially trapping humanity on Earth. Freezing without air. Space itself is not cold in the traditional sense. It has no temperature. But without an atmosphere, there is nothing to retain heat. Any exposed object slowly radiates its warmth away into the void. On airless worlds like Triton, surface temperatures drop below -230 degrees Celsius. Even the most advanced spacesuits cannot withstand such extremes for long. Exposed to these conditions, the body does not freeze instantly. Instead, systems shut down gradually. Heart rate slows dramatically. Blood thickens. Nerve signals fail, leading to numbness rather than pain. Consciousness would fade as oxygen delivery collapses. Within 1 to 2 hours, the body would freeze solid, preserved in place by the absence of air. When the body boils. If a spacecraft hull or spacesuit is punctured, the sudden loss of pressure triggers a phenomenon called ebolism. Liquids within the body begin to boil, not from heat but from lack of pressure. Saliva foams, tears vaporize, skin swells as gases expand beneath it. Air trapped in the lungs expands violently, tearing delicate tissue if the victim holds their breath. Oxygen bubbles enter the bloodstream, blocking blood flow to the heart and brain. Loss of consciousness occurs in under 15 seconds. Brain damage follows rapidly. Death arrives soon after. Oxygen loss, suffocation in seconds. Even without explosive damage, a slow oxygen leak is deadly. In space, pressure differences cause air to escape rapidly. As oxygen levels drop, cognitive function collapses first. Judgment fails, vision narrows. Panic intensifies the body's oxygen demand, accelerating collapse. Muscles weaken, coordination disappears. Unconsciousness follows within seconds. Without intervention, brain death occurs shortly afterward. Black holes, the ultimate end. Black holes represent the most extreme gravitational environments in the universe. Their pull is so strong that once an object crosses the event horizon, escape becomes impossible. As a human approaches a black hole, gravity stretches the body unevenly. Feet are pulled more strongly than the head, elongating the body into a thin strand. A process known as spaghettification. Bones snap. Organs tear. Time itself behaves strangely. Pain would be brief if felt at all before the nervous system is destroyed. Beyond the event horizon, nothing remains, not even information. Why space remains lethal? Despite technological progress, space remains fundamentally hostile to human life. Every breath depends on machinery. Every movement relies on precise engineering. And every mistake is final. Space does not forgive. It does not warn. It simply enforces its rules. That reality is why every space mission remains one of the most dangerous endeavors humanity can attempt.